Welcome to this presentation. You are watching Vlsi Design Lecture Series. Today we are going to speak about domino logic. A domino logic model consists of an n-type dynamic logic block followed by a static inverter. It is during pre-charge, the output of the n-type dynamic gate is charged to VDD, and the output of the inverter is set to 0. And during evaluation, the dynamic gate conditionally discharges and the output of the inverter makes a conditional transition from 0 to 1. So if one assumes that all the inputs of a domino gate are outputs of the other domino gates, then it is ensured that all inputs are set to 0 at the end of the pre-charge phase, and that the only transitions during evaluation are 0 to 1 transition. Hence, the formulated rule is obeyed here. So, the introduction of the static inverter has the additional advantage that the fan out of the gate is driven by a static inverter with a low impedance output, which increases the noise immunity. Also, the buffer reduces the capacitance of the dynamic output node by separating internal and load capacitances. Finally, the inverter can also be used to drive a bleeder device to combat the leakage and charge redistribution. And now you can see the concept of domino logic here. So mainly the domino logic avoids the cascading problem which arises in the dynamic block. The cascading problem arises because the outputs of each gate and thus the inputs to the next stages are pre-charged to 1, and this may cause inadvertent discharge in the beginning of the evaluation cycle. Setting all the inputs to 0 during pre-charge addresses this concern, and when doing so, all transistors in pull-down network are turned off after pre-charge. So no discharging of the storage capacitors can occur during evaluation. In other words, correct operation is guaranteed as long as the inputs can make only a single 0 to 1 transition during the evaluation period. So transistors are turned on only when needed and at most once per cycle. A number of design styles complying with this rule have been considered, but the two most important is the domino logic and NP domino. Right. Now you can consider the operation of the chain of domino gates, and during pre-charge, all inputs are set to 0. During evaluation, the output of the first domino block is either stays at 0 or makes it 0 to 1 transition, affecting the second gate. This effect might ripple through the whole chain and one after the other, similar to a line falling dominoes, and hence the name. And domino CMOS has the following properties. One is, since each dynamic gate has a static inverter, only non-inverting logic can be implemented. Although there are always there are many ways to deal with this, but major limiting factor is and pure domino design has thus become rare. And second point is, the very high speeds can be achieved with domino CMOS logic. Only a rising edge delay exists, and while TPHL equals 0. The inverter can be sized to match the fan out, which is already much smaller than in the complementary static CMOS case, as only a single gate capacitance has to be accounted for per fan out gate. Since the inputs to a domino gate are low during pre-charge, it is tempting to eliminate the evaluation transistor because this reduces the clock load and increases the pull-down drive. However, eliminating the evaluation device extends the pre-charge cycle. The pre-charge now has to ripple through the logic network as well. Consider the logic network shown here, where the evaluation devices have been eliminated. If the primary input N1 is 1 during evaluation and the output of each dynamic gate evaluates to 0, and the output of each static inverter is 1. On the falling edge of the clock, the pre-charge operation is started. Assume further that N1 makes a high to low transition. The input to the second gate is initially high, and it takes 2 gate delays before N2 is driven low. So during this time, the second gate cannot pre-charge its output as the pull-down network is fighting the pre-charge device. Similarly, the third gate has to wait until the second gate pre-charge before it can start pre-charging. Therefore, the time taken to precharge the logic circuit is equal to its critical path. Another important negative is that extra power dissipation when both pull-up and pull-down networks are on. Therefore, it's a good practice to always utilize evaluation devices. A major limitation of domino logic is that only non-inverting logic can be implemented, and this requirement has limited the widespread use of the pure domino logic. There are several ways to deal with it. One approach to the problem is recognizing the logic using simple Boolean transforms such as De Morgan's law. Unfortunately, this sort of optimization is not always possible, and more general scheme have to be used. A general but expensive approach to solving this problem is the use of differential logic, that is dual rail domino is similar to the concept of DC VSL structure, but it uses a pre-charged load instead of static cross-coupled PMOS load. And you can see NAND differential logic gate. Note that all the inputs come from differential domino gates and they are low during the pre-charge phase while making a condition 0 to 1 transition during evaluation. Using differential domino, it is possible to implement any arbitrary function. This comes at the expense of the increased participation since transition is guaranteed every single clock cycle regardless of the input values. Either 0 or 0 bar must make a 0 to 1 transition. The function of the transistors M1 and MF1 and MF2 is to keep the circuit static when the clock is high for extended periods of time. It is called as bleeder. So you can notice that this circuit is not ratioed even in the presence of the PMOS pull-up devices. Due to high performance, this differential approach is very popular and is used in several commercial microprocessors. So when clock is low, dynamic node is pre-charged high and the buffer output is low, PDN is the next logic block will be off. And when clock is high, dynamic node is conditionally discharged and the buffer output will conditionally go high. Since discharge can only happen once, buffer output can only make only one low to high transition. When domino gates are cascaded, as each gate evaluates, if its output rises, it will trigger the evaluation of the next stage and so on, like a line of dominoes falling. Like dominoes, once the internal node in a gate falls, it stays fallen until it is picked up by the pre-charge phase of the fire next cycle. Thus, many gates may evaluate in one evaluate cycle. And one of the main disadvantages of the domino logic is charge sharing between the nodes in the pull-down network, and the dynamic node can unintentionally reduce the voltage of the dynamic node enough to switch output buffer. In addition to the output inverter makes domino gates non-inverting. Some circuits cannot be implemented solely using domino logic unless both polarities of the inputs are available. So this diagram shows the example of a domino AND gate. So as I said earlier, the dual rail domino logic is which solves the problems of true and complementary inputs, and it produces both the true output and complementary outputs. So dual rail domino gates encode each signal with a pair of wires. The input and output signal pairs are denoted with H and L respectively. So this table summarizes all the encoding. The H wire is asserted to indicate that the output of the gate is high or 1. The L wire is asserted to indicate the output of the gate is low or 0. When the gate is pre-charged, neither H or nor L is asserted. The pair of lines should never be both asserted simultaneously during correct operation. So this diagram shows the dual rail domino logic for various logic functions. And with a footer transistor, the dual rail domino logic is tabulated here. It accepts both true and complementary inputs and compute both true and complementary outputs. So you can observe that it is identical to static CVSL except that the cross-coupled PMOS inverters are instead connected to pre-charged clock. Therefore, dual rail domino can be viewed as a dynamic form of CVSL, and sometimes it is also called as DCVS. So what you see here is the diagram of a dual rail AND NOT and XOR XNOR gates. The gates are shown with clocked evaluation transistors but can also be unfiltered. Dual rail domino is a complete logic family in that it can compute all inverting and non-inverting logic function. However, it requires more area, wiring and power. Dual rail structures also lose the efficiency of wide dynamic NOR gates because they require complementary tall dynamic NAND stocks. Dual rail domino signals not only the result of a computation but also indicates when the computation is done. Before computation completes, both rails are pre-charged. When the computation completes, one rail will be asserted, and this is particularly useful for asynchronous circuits. Thank you.